make whole conversations or try to
Alright, so what's the probability that you can earn 1? Let's probably pick earn 2. And earn 3. Now, let's probably pick a black, this way is, I think earn 2, you can get what? Red or blue, black. What's probably a red? 5 and for black. Alright, and then earn 3, red or black. What's probably red? 6 and black. Now, to get here, I need to multiply along the branches. Because this is, to get here, it's 4/5 of 1/3, right? How do you multiply? So it's going to be, oops, 1/3 times 4/5, and you guys end up getting, like what, 0.267, is that right? And then here you did 1/3, we care about all the red ones, right? Because we care about getting red marbles. People are scratching and confused. All right, so since there's a lot of people putting their heads down and writing, I'm going to take a small break and let you guys finish that. Okay, so you guys should end up with 1/3 times 3/5, 0.200, and 1/3 times 3/6, 0.167, I think. Okay, so now what do I do? How can I get a red ball? I can get one from earn 1. How else can I get it? Or from earn 2, or from earn 3, or as we what? Add. Or as we what again? Add. So we're going to add these. Does that make sense? Earn 1 or earn 2 or earn 3. Add them, and you'll get 0.634, I think. Now, if you'd done it where you did it all by fractions, then you'd end up with 0.633. That's fine. This is just due to rounding. If you're off a little bit in this very last spot, that's not a big deal. That's why we go 3 decimal places, so that you're still quite accurate. Okay? Okay, I do want to go over the next one briefly. Okay, you're rolling 2 standard dice, and you add the numbers. What's probably getting a number larger than 9 for the first time on the 3rd roll? Yeah.
I have a question about the last problem.
Yes, please, go ahead.
So, why don't we just look at the whole pool of red balls and black balls and then count them?
Because they're not equally likely to be chosen.
Okay.
The ones that there's 6 of them in the urn, they're less likely to be chosen than the other ones because there's more of them to compete for in that urn.
Even though it doesn't matter which urn.
Okay, so think about it like this. Urn 1 has a black ball in it.
Yeah.
Urn 2 has a black ball in it. Urn 3 has 100 red balls in it. If you used it ball by ball, then the reds would be 100 out of 102.
Okay.
Do you see what I'm saying? And that's not right because there's 2/3 chance you're gonna pick earn 1 or 2 and get a black ball. So that can't work. Okay. Now I'm rolling 2 standard dice, but I love the fact that you're thinking about it because that's good. That's a great question. All right, roll 2 standard dice and add the numbers. What's the probability of getting a number larger than 9 for the first time on the 3rd roll? Okay, so someone asked me last class and said, well, probably of getting a number larger than 9, there are 6 ways of doing that. So larger than 9, there's 6 ways out of 36 of doing that. All right, so 1/6. So his question was, well, if it's for the 3rd time, wouldn't it just be 6 out of 36 and the first 2 rolls don't matter? If we said, what's probability of getting a number larger than 9 on the 3rd roll, that would be true. But yeah, but it's not just the third time. It's for the first time on the third roll. So if you did it for the first time on the third roll, that means if you do it if you did it for the first time on the third roll, does that mean did you do it last roll? No. Did you do it the roll before that? No, because you did it for the first time on the third roll. That means the first roll, you failed to do it. And the second time, you failed to do it. Does that make sense? So that means that, here's your situation. You've got 3 rolls. It went fail, fail, succeed. Does that make sense? Okay, so I'm going to give you guys a minute to think about that. And then we'll take a break. Let's take a break until, let's see, it's 13 after until 23 after, and then we'll come back and go through this. Okay, so success, we said that was succeeding, there was a 1/6 chance that I succeed, right? 6 out of 36, which means that what's the probability that I don't succeed? 5 out of 6. Suppose it's 5 out of 6. And again, is it that the first? I'm failing on the first one, and I'm failing on the second one, and I'm succeeding on the third one. All 3 of these things have to happen, right? So I'm saying the situation is that I had to have failed on the first one, and failed on the second one, and succeeded on the third one. That's the situation. And we what? Multiply. So, and you know what? Everybody say and to multiply. Ready? 1, 2, 3. And to multiply. Good. We need to make sure you really get that stuck in your head before the exam. And then you guys end up getting, what do you guys get? 0.116. Anybody else?
Yep.
Okay. Seems good. I got confirmation for one person. Anybody else?
Yeah.
Okay, good. Okay. So I think this is just emphasizing the part about a tree. So again, when they're dependent, you can totally draw a tree and still get these probabilities. So here, yellow male independent. My first step, I can make my first step yellow, so I know it's a yellow puppy. It's a yellow lab. Then, yellow lab, given that it's a yellow lab, the probability that it's male. But you're coming from a spot where you know that it's yellow. So it restricts how many puppies you're talking about. So here, which one do you want me to do first? Yellow, the color of the puppy, or the gender of the puppy?
Gender.
Gender, okay. So we got male pups and we got female pups. How many male pups are there? 12. So probably I pick a male puppy as what? 12 out of 20. Right? Everybody on board? So the female is 8 out of 20. Now, if I pick a male puppy, it could be a yellow lab, a chocolate lab, a black lab, or a yellow lab. Everybody on board? What's the probability it's a chocolate lab? Well, I know for sure I picked a male puppy because I'm standing right there. If I'm standing right there, then how many male puppies are there? 12. There's 12 male puppies. So I know it's out of these 12.
Is this on the notes or?
No. This is me trying to explain stuff to you so you're not totally lost in a week when you take the exams. All right, so you guys, I need you guys to settle down. If you guys need to talk, go outside and talk, that's fine. But I can't have you guys messing up other people who are trying to learn, right? It's not fair to them. So there are 8 male puppies. So I know it's out of 8. What's the probability that it's a chocolate lab? Sorry, I know that it's 12, my bad. There are 12 male puppies. 8 out of 12? So there are, let's try it this way. I know it's a male puppy. What's probably it's a chocolate? 5 out of 12. What's probably it's a black lab? 3 out of 12. And yellow lab? 4
4 to 12.
4 out of 12. Great. And I can do the same thing down here. Now, how many female labs are there? Now there's 8. So the probability that given it's female means 100% chance you know it's female. Right? So if you're given something, the probability of it being there, 100%. That means I am here if you're given that. So given it's female, what's the probability that it's a chocolate lab? 3 out of 8. Black lab? Yellow lab. So if I asked you on a side question, if I were to ask you, find the probability of chocolate given female, what would that be? Yeah, right there. Because 100% I know it's female. I'm given that. So 100% chance you're right here. If you're right here, what's the probability that you pick a chocolate lab? 3 out of 8. Everybody okay with that part? Yeah. So if you don't have the table, you can still find this just off of the tree. All right, so now you guys have one. Problem 11, so flip backwards to lab problem 11. It is on the 8th page. Automobile insurance. Good. Got it? Does anybody need the notes for chapter 4? There's a copy over there if you need them. Okay. Insurance company has low risk, medium risk, and high risk drivers. They find that 1% of low risk drivers had an accident, 5% of medium risk drivers had an accident, and 9% of high risk drivers had an accident. Find the probability a driver will have had an accident. So, you need to draw a tree. As a hint, I'm telling you, use risk as your first set of branches. How many options are there for risk? 3. Good. For your probabilities, write them as decimals. Do not write them as percents. 60% should be 60 cents. Right? 0.60. The other thing I'm going to ask you is, okay, if 1% had an accident, well, what's the other option?
No accident.
No accident. If 1% had an accident, what percent did not have an accident? 99%. Good? And those are conditional, right? 1% of low risk. So it's given a low risk, then that's 1%. All right, so take a look, and again, write them as decimals. It'll make your life easier when you multiply them. Okay, let's see where you guys are at with this. So, first we have, what is it, medium or low? Which one's first? Low? Low, medium, high?
Yeah.
Okay, what's probability went to low?
0.60.
0.60. All right, 60% are low. How about medium?
0.30.
And high?
0.10.
Great. Now, if I'm low risk, I can have an accident or no? What's probably have an accident? 1%. 1 cent. 0.01. All right, not 0.1, 0.01. 1 cent. 1% is 1 cent. Which means 99% chance I don't. How about medium?
5%.
5%. 5 cents. 0.05. Which means 95% I don't. And high risk? 9%. 0.09. Okay, we care about these outcomes, right? The accident outcomes, yeah? So, what's the probability? So how do I find that? Multiply along the probabilities, right? 1% had an accident. 1% of 60% of the people. Means multiply. 0.60 times 0.01, 0.006.
What?
0.30 times 0.05, 0.015. 0 times 0.09. There's, you guys are really quiet. Okay. Now, how might someone have gotten in an accident? They could be in an accident and been a low-risk driver. What's another way?
Medium risk driver or high risk driver.
Or high-risk driver. Or low or medium or high risk. Or as we what? Someone say it together. Or as we add. Ready? 1, 2, 3. Or as we add. Get used to saying it. Write it down. Tattoo it on your forehead. Well, not your forehead, but yeah. But write it somewhere where you can wake up in the morning. Maybe tape it above next to your bed. Or means add. And means multiply. So before you go to bed, you see it. When you wake up in the morning, you see it. That way, in the next week, when you come to take a test on Thursday, you'll remember it. Right? Okay. So we're going to add these. Good? 3%. Good? All right.
Isn't that 30%?
No. 0.03. 3%.
I thought it was in the 10th spot.
Oh yeah. This is the penny spot, so that's your percents. 3%.
Oh, I get it.
Right? Cents percent.
So if it was 0.3, would it be 30?
Then it would be 30.
Okay.
All right. We will talk about bays later. Lab 1. There are. We do not have time for that.
Yeah, let's skip it.
Okay, we'll get to it next class. We do have time for this one though. So the next, like halfway down the next page, is lab problem number 3. I really feel that you guys really do need to do lab problem 1. If you don't do it, it's going to be trouble before the exam. So we definitely need to do that next class. All right, lab problem 3. At a gathering consisting of 8 men, 17 women, 2 door prizes are awarded. Find the probability that both are won by men. The winning ticket is not replaced. Okay, how many people are there?
25?
25 people. Okay, what's the probability that the first person drawn is a man? 8 out of 25. Great. I draw a ticket. I do not replace it. Now, how many men are left?
7.
Out of how many total people?
25.
24. You've drawn one, right? Now there's only 24 people left. So it's probably the second person is a man. All right, so now do I need just one of them or do I need both of them to have gotten this? Both. So both means and we what?
Multiply.
Great. I would say it, and we multiply.
And we multiply.
So we're going to multiply these. What do you guys get?
Is there a name?
Perfect. Okay. What's my guideline? What's our guideline for unusual? 5% or less? Is this unusual? No, it's not 5% or less. It's 9 cents, like it's roughly 9%, 9.3%. Likely. Not 5% or less.
I think on the homework, there was a problem that was similar to this. It said, it had the question at the bottom that said likely or unlikely.
There's one that's wrong.
And I think that one was wrong because I put unlikely, or I put likely. but
Yeah.
likely.
Yeah. So there's a couple of them that are. So your textbook is a great textbook. It is fraught with errors. So just if you get the right answer and it marks it wrong and you know it's right. So you guys, heads up. if you get the right answer in the homework and you know it's right and it still says it's wrong, take a picture of it and send it to me. I take a screenshot of it and send it to me, and I'll check and I'll always say, no, 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 you got to consider this, or I'll say thank you, and I'll forward it on to our rep to hopefully get fixed. Because there are definitely errors in it. Okay. We are going to skip that part. We're going to jump straight into, we'll do law of large numbers. Okay, so law of large numbers. Here's the deal. If you flip a coin 10 times, how many heads do you expect to get?
About 5.
About 5. Okay, good. But you might get 4, 6, stuff like that, right? But what the law of large numbers says is that as you perform an experiment, like flipping a coin over and over again, thousands of times, then the probability of heads you're getting is getting closer and closer to 50%. What it does not mean is that if the coin has come tails the last 4 times, that's more likely to come heads next. The next flip is still 50-50. The coin doesn't say, oh, wait, I just came tails, 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 it's time for me to come heads. Each flip is still 50%. What it's saying is, if you do it thousands of times, then they'll even out over time. It's a law of large numbers. As it becomes really, really big, it just starts sort of tending towards what it really should be. All right, not a big deal. The moral of that story is, do not go into the casino and say, oh, people do all, they used to do all this time on the back of the table I dealt. They'd be like, they'd rush to your table, because if it went player, 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 they'd rush over and put a big bet on banker, because it must come banker next. It just came player the last 6 times. Still 50-50. I would tell you a great story about it, but we're kind of short on time. Maybe do the review session, ask me. Okay. Now we're going to flip over to the, well, it wasn't a great story. I lost like $700. All right, so we're going to flip over to page 10 at the very bottom, counting, chapter 4.4, 4.5. Okay, the fundamental, I'll say it again so you can write it down. The fundamental principle of counting. Fill it in. It says that the total number of possible outcomes of a series of decisions is found by multiplying the number of choices for each decision. For example, if I have 2 pairs of pants, 3 shirts, 5 shoes, and 4 socks, I have 2 times 3 times 5 times 4 possible wardrobe combinations. This is the exact same solution we would get if we used a tree diagram. Only it's a lot less work, though it won't give us like every single possible outcome. So for example, we could do a tree, and the first layer of branches would be pants. The second layer of branches would be shirts. And now for each one of those, we'd have 5 for shoes, and so forth. Let me show you what I mean a little bit. Right? So here, right, first layer of branches is jeans, or slacks, pants, right? So there's 2 options after that. The next one is shirts. There are 3 options for shirts. So there's a group of 3 off of here. How many groups of 3 do I have? 2, because I had 2 pairs of pants. Does that make sense? So now I have 6 possible end branches. Does that kind of make sense? You guys with me? Mm-hmm. 3 for the shirts, but 3 times 2 because I had 2 pairs of pants. So now I'm at 6. Now if I did shoes off of that, 5 shoes, it would be boom, 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 5 shoes. So 5 possibilities, but how many times do I have 5 possibilities? 5 there, yes, 6 times, because I'm going to do that for every single one of these. So all of a sudden it's going to be 5 times 3 times 2, right? So that's kind of where this all comes from. You guys try. You have 2 pants, 6 shirts, 3 shoes, and I don't know, 5 socks. How many possible wardrobe combinations? It's not on your sheet. I'm just asking you. All right. So how many pants options?
2.
Shirt options? 6. Shoes options? 3. Socks? 5. What are you going to do with them?
Multiply.
Multiply. Okay, so here's to make your life easier. You see a 2 and a 5, grab them immediately and set them aside. Because 2 times 5 is 10, so that means you just add a 0 at the end of your answer. 3 times 6 is what? 18. Boom. Done. Right? So much easier. All right. Now, let's get down to reality. On a test, how do you remember that you need to multiply instead of add? This is how you do it on a test. You create a simple situation that you know the answer to, like 4 shirts and 2 pants, and draw a little tree for that. 2 pants, 1, 2, 3, 4 shirts, 1, 2, 3, 4 shirts, and you say, oh, there's 8. So are you guys kind of following me? And then you say, okay, I get 8. Is that 4 plus 2? No. Oh yeah, that's 4 times 2. I need to multiply. That's how you remember. It's by creating a situation that you know you can control, figuring it out, and then applying that to the larger situation. All right. Do problem number 5 on your lab. Next page. Pick a 3-digit security code. You can pick 0. 0, 0, 0 is totally fine. How many possible codes?